This is Rich Taylor, Miami University, and the topic of this presentation is extraction using phase separations in order to purify compounds. Throughout an organic chemistry course, students learn a variety of techniques. The overall goal is to relate the lecture equation so that the student has an actual idea of the physical operations that occur in order for that reaction to result in the listed product in the equation. In practice, reactions are often, almost always, carried out in some sort of a solvent, and the product is usually obtained as a mixture. There may be recovered starting material, there are going to be byproducts of the reaction, that solvent's going to be left over. The ultimate goal of a reaction is to actually isolate the desired compound in a reasonably pure form. Extraction is a good way to begin approaching this process. So a reaction is often the first step in going from a really crude mixture of lots of compounds in fairly significant amounts to beginning to get down to a single compound in more or less pure form. Following extraction, then, other techniques such as chromatography, recrystallization, distillation, and the like are going to get to a more pure compound. So extraction is the first gross separation in the beginning of that process. The crucial concepts that play into understanding extraction are phase separation, partition, and side issues that come on with that and also inform the process of extraction are an ability to understand solubility in water as a function of pH, and also the crucial role that the density of liquid plays in doing a successful separation. The first technique we'll look at is solid-liquid extraction, where the two phases are a solid phase and a liquid phase. Let's just consider a hypothetical. Suppose you had a mixture of salt and sand. How would you get the salt away from the sand? Well, one way would be to get a magnifying glass and tweezers and look at each particular grain and make two piles. That's not terribly efficient. A more efficient way would be to put the entire mixture of salt and sand in a bucket and add water. Swirl it around with a stick for a while, and what you'll find is that there's then partition between two phases. There'll be leftover solid, and there'll be a liquid phase. If you filter those two phases away from one another, what you'll find is that all the salt dissolved in the water. And so what you would have is the liquid that you've separated away would be salt water. Presumably you could evaporate away the water and then have salt reasonably pure. And then the solid's going to be wet sand, which then when it dries out is going to be pretty much pure sand at that point. That's the essence of a solid liquid extraction. Another example is making a pot of coffee. You take ground coffee, put it in the coffee maker, and the coffee maker pours hot water through the coffee that's ground up. And so what you then have is, once again, a solid liquid partition. The solid that's left behind is coffee grounds. You throw those away. The liquid's coffee. Coffee's not a single pure compound, but you've separated the things that are not water soluble in coffee beans from the material that we then call coffee. If you want the individual components of coffee, then you have to do further separations, but this separates the water soluble materials from the things that don't dissolve. A liquid-liquid extraction is usually the first step in a standard organic reaction. What's required to do a liquid-liquid extraction is two insoluble liquids. One of these is almost always water, and the other is going to be an organic solvent. Good examples of a partitioning extraction might be water and hexane. Hexane could also be petroleum ether, which is a mixture of hydrocarbons, but they fulfill the same purpose. You might have partition between ether and water, ethyl acetate and water, dichloromethane and water, and many others. The important criteria is that they not be soluble in one another. So water and ethanol won't work. They mix completely. Water and acetone won't work. They mix completely. So you have to have phases that are immiscible. What you're then going to do is mix the material to be purified with water and an organic solvent in a separatory funnel, swirl those around and allow the layers to separate. There'll be an organic layer, and an aqueous layer, the water layer, and different molecules will be differentially solubilized in the two layers. Like dissolves like, so the polar and ionic compounds will mostly dissolve in the water and be in the water phase. Organic solvents are much less polar, and so the organic materials, which are also less polar, will dissolve in that organic solvent. You can then separate the layers and separate polar from nonpolar materials. There's a mock-up of a separatory funnel. Should make a note here that that stopcock needs to be closed or the liquid's going to flow straight out of there. But in there then you'll place the organic solvent, the water, and the compounds you wish to partition. And you'll take these, put them all in there, stopper up the top, and then invert it. This will be stoppered, and when you open up the stopcock to allow vapors to equalize, you can then swirl this thing around, close the stopcock, put it back upright, the layers will separate, and then you can use the stopcock to drain the aqueous layer into one flask, the organic layer into another flask, and you've separated the two phases. When we talk about partition then, we recognize that some things are more likely to wind up in the organic layer, some things are more likely to wind up in the aqueous or water layer, but the partition is not going to be complete. The organic solvent is going to be wet, and it's also going to have some polar materials in there, and so at the very minimum you're going to need to dry this, usually using magnesium sulfate, and then use gravity filtration to get a dry solvent that has your organic material in there. The aqueous layer is going to have some organic components in it as well. We can define these by terms of a partition coefficient, which is the concentration of the compound you're interested in the organic layer divided by the concentration of the compound that's in the aqueous layer. Obviously, you would like your partition coefficient to be either 0 or infinity in order that the material you want is completely in one phase and not the other, but you're not going to necessarily get that. Many of the reactions that are done in the organic lab are pretty close to that, so you don't need to do multiple extractions, but it'll never be perfect. The consequences of the partition coefficient then is that the partition coefficient is a function of the organic solvent you chose. So you can choose an organic solvent to optimize your partition coefficient, and also you can do multiple extractions so that if the material you're interested in is mostly in the organic layer, you can extract that aqueous solution several times to try and milk as much of the compound you want out of that aqueous layer. If you play around with the equations from the partition coefficient, you'll find that several extractions with small amounts of organic solvent is more efficient than one big extraction with the same amount of liquid. So multiple extractions with small amounts of material is typically the optimum way of getting your compound out of the aqueous layer.